Hello, it's Scott Manley here. In my most recent Deep Space update video, I made a comment about Apple's satellite SOS service being available in North America and Canada. And of course, everyone in Canada decided to remind me that yes, Canada is in fact in North America, and I did in fact know that. In fact, I am actually partly Canadian. I had an ancestor that moved to Canada and then came back to Scotland. But look, what I really want to do is make it up to you Canadian space nerds by talking about the world famous Canadarms. So let's rewind in history, right? So in the mid 1970s, Canada had the opportunity to participate in the US Space Shuttle program. Canadian engineers had already developed things like compact deployable antennas, which were commonly used in American spacecraft. Canadian scientists had built and flown satellites. Their engineers had also developed a robot arm for refueling the CANDU nuclear reactors. And NASA looked at this and said they really wanted a versatile arm for working with payloads on the space shuttle. So in 1974, Canada signed on to develop the remote manipulator system for the space shuttle program. This was before the Canadian Space Agency actually existed. This was another research agency that handled it. So ultimately, the arm that was developed for the space shuttle was 15 meters long with two main sections made of carbon fiber tubing, about 33 centimeters in diameter or 50 feet long and 13 inches wide. The arm is covered with Kevlar blankets to protect it from impacts and micrometeoroids and to control the temperatures while in space. The arm is described in anthropomorphic terms, with the base being the shoulder, providing two axes of rotation. The elbow halfway down has a single axis of rotation, and then the wrist has full three axes of rotation with yaw, pitch, and roll. So these joints are all driven by small motors driving gearboxes to rotate them. And the whole arm motion uses only a few kilowatts of power. I mean, it's said that it's less power than it takes to boil a kettle. In each of the joints, there's also encoders so that they can provide feedback and measure the rate of motion. And there's a pair of TV cameras, which can be used by the operators. And finally, at the far end, instead of a hand or a claw, there is a tubular-shaped end effector, which uses a wire snare system to mate with the corresponding grapple fixtures, which have to be incorporated into the payload design for them to be manipulated. So I'll talk more about the end effector design later. But anyway, while this arm was designed to manipulate objects massing almost 30 tons, it was pretty lightweight. It had a launch mass of less than 400 kilograms, less than half a ton. But even then, it was designed for zero gravity, and it couldn't lift its own weight against Earth's gravity. So during ground testing, they would have it supported by various systems, such as this low friction air table, which was used to show the elbow operation. The first flight test of the Canadarm was on the second Space Shuttle flight, crewed by Joe Engle and Dick Truly. It was supposed to be a 5-day flight, but early on there was a problem with one of the fuel cells, which necessitated cutting the mission short and losing the chance to test the arm in space. But they had to wait the better part of a day for the Earth to rotate back to the correct orientation so that the Space Shuttle would be able to return to the landing site. And in that time, the crew were supposed to get some rest. After all, this was a very special re-entry with Joe Engle playing full-on test pilot and manually flying large sections of the entry rather than letting the computer do it. But during much of that time they were supposed to rest, the shuttle would be, well, it would basically have no communications with the ground, right? This was before the days when we had satellites up in geostationary satellites. The TDRS network, which now enables the space station to basically have more or less continuous communication. So without this, the shuttle had to communicate via a limited number of ground stations, and when it wasn't near those, it wasn't talking to anyone. So instead of resting, the crew disobeyed the orders and carried out tests on the arm during the periods when they were incommunicado, right? And during this time, the test, they were able to demonstrate the arm under both manual and computer control. And an important part of controlling robot arms is like the automation which allows the operator to command motion from the end effector's point of view. Right, so basically if you push the joystick forward, it moves the hand forward and it figures out what all the intervening joints should actually do. So This was all tested and everything operated as expected, and the crew even used the cameras to take an image of themselves controlling the arm and saying, "Hi, Mom." So yeah, they completed the tests and then they flew the return to Earth with the test program and everything, and they landed at Edwards Air Force Base on day 2. So the arm would then be tested further on Space Shuttle Test Flight 3 and 4, and eventually NASA liked it enough they decided that they would order 4 more arms for the rest of the shuttle fleet that they were planning to build. One of the arms would end up getting destroyed with Challenger, and the arms weren't carried by default on every flight. They didn't always fit into like mission requirements, right? Not every mission had a specific job that the arm would be required to do, but sometimes they would be carried even if the mission didn't call for it, since they were actually useful for all sorts of contingency procedures. Like there's one case where you would have to perform an EVA to get underneath the shuttle and close the umbilical doors, and having an arm would definitely help in that case. The arm would also have been an ideal tool to inspect the effects of the foam strike on Columbia during its fateful mission. But that was a space lab mission, and they didn't have any need for the arm on the experimental list, and there were other missions that were needing the arms for ISS development, so the crew of Columbia didn't have the hardware with them, so they didn't have a chance to see the hole, and that definitely ended up, contributing to the mission's, end. So after the Columbia disaster, the arm became a standard part of every flight, and because it was part of the heat shield inspection procedures. Now, the arm as it was built wasn't long enough to basically see all the way under the belly of the space shuttle. So they developed an extension of the arm. And this was actually made from spare Canadarm parts, but it was a rigid version with no joints. It was called the Orbiter Boom Sensor System. And it could be picked up by Canadarm, and in that, if you picked it up the right way, it would effectively double the length of the arm, allowing the sensor system to scan the entire heat shield using cameras and lasers and LiDAR and everything. So now, how does the arm actually grasp objects? Well, the end effector uses a set of 3 wires on a pair of rings, and in one orientation the wires are stored in the wall, and as it turns it pulls the wires into the middle. So the grapple fixtures on the target have like a pin sticking out with a pin at the end, and the end effector basically roughly aligns with this pin, and then the snare motor will rotate, the wires will pull in, get looped around the end of the pin and tighten, and that pushes the pin into the middle of the effector. So at that point this payload is snared, but the connection is still somewhat free to rotate, and the interface needs to be made rigid before the arm can be used to move the payload around. So the next thing is, inside the effector they have a ball screw which retracts the snare assembly, pulling that pin inside the effector until the base of the grapple fixture mates with the front side of the end effector, and that's forced into a rigid alignment by 3 grapple cams in the base of the grapple fixture, which align with cutouts in the end effector. So the whole process is actually pretty fast. It had to be fast enough so that it could grab free-flying payloads while, say, the shuttle was holding position relative to the target, or say while a cargo spacecraft is sitting close to the space station. Once capture is completed, the arm can move the payload around, but it does this very slowly. While 0G means that the object has no weight, it will still have inertia. And for heavy payloads, the operator really has to account for the acceleration and deceleration. While it was originally designed for 30 tons, they would actually later upgrade it with software that would allow it to move masses of 100 tons, more than the mass of the space shuttle itself. And while it was often used for large payloads like the Hubble Space Telescope or space station modules, one of the more common things that it actually carried was astronauts who could ride a platform on the end of the arm so that they would have a stable platform to work from during EVAs. Now, beyond the basic grapple fixtures, which would just ensure solid lock, there's more capable versions that were developed for various tasks. Like There's a latching fixture which has extra latches around the edges, so after they put it and lock it in place, these latches can attach and it reduces the strain on the wire system and is a much more rigid connection. And then there's two different variants with connectors for power and video, or power and data, which in addition to those extra latches. And it's also worth mentioning that the pin and alignment cams that are used by this system are the same as used by the Japanese robot arm on Kibo. So those systems are technically compatible with them. But there's also, like, the Kibo design has an extra power and data port that's specific to that design that isn't found on the Canadarm designs. So now, moving on to the 21st century, for the International Space Station, Canada were of course the first choice for the bigger and better arm, the Canada-2, the sequel, the Canada-ing. The space station's arm is bidirectional. That means it has 3 degree of freedom wrist joints at both ends, and the end effectors are the kind that incorporate power and data connectivity at both ends. So the arm can move to different locations on the station depending upon the needs of the task. So it can move one end to grab the anchor point, lock into that, and then detach its original point and move around the station in that. As long as there's a power and data fixture in the correct location, it can reach where it's going. In addition to this, the arm pretty much lives on this mobile service platform which moves along the truss structure on rails. Canadarm 2 also has some other upgrades. It has a force sensors now to measure the forces being applied to it, and that allows more control when it's moving masses around. It can sense the mass on the end and adjust the way that it's pushing to make sure that the payloads are being moved as efficiently as possible while not compromising safety with the arm's capabilities. Canadarm 2 would be delivered to the space station in 2001 on STS-100, and so it was actually available for the majority of the International Space Station construction missions. New modules would actually be routinely handed over from the shuttle's Canadarm to the station's Canadarm, which was affectionately referred to as the Canadian handshake in space. And Canadarm 2 got the Canada hand. This is a special purpose dexterous manipulator, or Dexter. This has 2 smaller arms on it and a rack of tools. So Dexter can be latched onto the end of the Canadarm, and it can be used for much more delicate operations than the arm alone. Dexter can actually be used to replace parts of the station which would otherwise require astronauts to perform an EVA, and it's even been able to service the Canadarm itself, replacing cameras and other modules over time. And perhaps more significantly, the entire Canadarm 2 system can be operated remotely by technicians on the ground. So all sorts of maintenance tasks can now be performed with minimal support by the astronauts on the space station. And this tends to happen at a slower pace, so when a task is time sensitive, say grabbing a dragon by the tail, the astronauts will operate the arm directly, usually from the operator station in the cupola module, which gives them a clear view of everything that's happening with their own eyes. The orbiter boom sensor system, which was used for the Space Shuttle heat shield inspection, it also got added to the Space Shuttle's set of tools. In 2007, STS-120 had reconfigured the space station, and when the solar arrays were unfolded again, some damage was seen, so they needed to do an emergency EVA to repair the panels. But to be able to reach the affected areas, the space station's arm would hold the sensor boom from the orbiter from the space shuttle and put an astronaut out on the end of it to perform the repair. So after this, NASA saw that there was great value in having this arm extension available, and so they came up with some design modifications to the boom which would allow them to be left on the station for future use. So the enhanced boom added the power and the data capabilities to the grapple fixtures, and it would be delivered on STS-134 in May of 2011. Essentially, Endeavour went up with it, used it to inspect its heat shield, and left its sensor boom up on the space station before returning to Earth. So now, the ISS is getting old, and we're looking to the next iteration of Canadarm, right? The Lunar Gateway is going to have another Canadarm, right? It's going to be smaller and lighter. It's going to have telescoping joints so it fits into a smaller space for transport, but it will be a lot smarter, and it will come with another small version of the precision arm with tools to enable even more remote work on the station, which won't have a crew on board for most of the time, so it really helps with station maintenance. So this is Canada's contribution to the Artemis program, and it's one reason we expect a Canadian astronaut to be the first non-US citizen to fly past the moon on Artemis 2. Now, Canada's contribution to the shuttle program, this arm, it did allow a number of Canadian astronauts to fly, including, of course, Chris Hadfield, who ultimately got to record Space Oddity in space. Therefore, I'm very grateful the Canadarm exists. I'm Scott Manley. Fly safe.